Hello everyone, welcome to another session on game theory. In the session so far, we have covered standard games in game theory, and we have also covered the concept of Nash equilibrium in the previous session. So in today's session, we will apply the concept of Nash equilibrium to solve the games that we have studied earlier. All right. So as you must remember, Nash equilibrium essentially is a steady state. It's an action profile that is steady in the sense that no player can make any increase in her payoff by unilaterally deviating from the equilibrium action profile, right? So if every other player is doing what the action profile or every other player is choosing the action that is specified for her by the action profile, then this player or whatever player from whose POV we are looking at, this player cannot make a unilateral deviation and be better off, right? So we discussed the example of people behaving outside the metro station and inside the metro station. Should that, if you could keep that in mind to understand any concept of equilibrium like that. All right. So now let us look at the games that we have done. We'll start with Prisoner's Dilemma, and we'll see how to like evaluate all possible outcomes, right? And see if they fit the definition of a Nash equilibrium action profile, right? So this is the crudest way. What we'll do is, say we have, let's start with, so we have, let's start with solving games. Okay, the first one that we will do, of course, is the Prisoner's Dilemma, and the way we will do it is that we will evaluate, we will look at each action profile, that means each outcome that is possible in this game, and we will see whether in this outcome any player can benefit by deviating unilaterally. If that deviation is possible, then of course it's not a Nash equilibrium. And if for an action profile such a deviation is not possible for any player, then that becomes the Nash equilibrium. All right. So this is what we had. We had quiet and we had Fink. This was player 2. This was player 1. Again, quiet and Fink, right? And quiet essentially gave you 2, 2. Here you got 0, 3, here 3, 0, and here 1, 1. So this was the game. We know that a lot of games are modeled like this. So let's look at each action profile over here. Okay. So the first action profile that we will evaluate is Q, Q. See, action profile, because it specifies an action Q for it specifies an action Q for player 1 and an action Q for player 2. For every player, it's specifying an action. Now, think in terms of unilateral deviation. So now, first of all, let's think from the point of view of player 1, right? So if player 2 is choosing the action that is specified by this profile, by this action profile, then then can player 1 benefit from deviating, right? So player 1 के पास यहाँ पे क्या option है? Suppose player 2 is choosing Q, ठीक है? तो हम इस zone में हैं. Player 2 is choosing Q, that means we are in this zone, right? This column is where player 2 is choosing Q. इसमें player 1 के पास we have two options, right? One is to stay quiet and one is to Fink. If player 1 stays quiet, which is what this action profile essentially specifies. So if she stays quiet, she gets a payoff of 2. Whereas if she Finks, she gets a payoff of 3. Right? So that means that this cannot be a Nash equilibrium. You can see that one player can make a unilateral deviation, that means the other player is still following her equilibrium strategy, right? But the first player can make a unilateral deviation and be better off. Instead of staying quiet, she could just Fink and she could be better off. right? And symmetric argument applies to player 2 also. You can try and do that. If you see, if you want to see the case where player 1 is choosing Q, right? So now we are thinking from the point of view of player 2. So player 2 is thinking कि अगर player 1 quiet रह रहा है, right? So then this is the zone that needs to be evaluated, right? This is the row in which player 1 is quiet, right? So then player 2 के पास obviously दो options हैं. One is to go with the equilibrium strategy, or the strategy specified by this action profile over here, right? That gives a payoff of 2, whereas if the player thinks, that gives a payoff of 3. दोनों player symmetrical हैं, होना ही था, right? So again, not a Nash equilibrium. In fact, to reject any action profile for a Nash equilibrium candidature, एक भी player का deviation दिखाना is enough. ठीक है ना? क्योंकि for Nash equilibrium, the deviation should not be beneficial for any player. So if it is beneficial for even one player, बाकी किसी का फायदा नहीं हो रहा है. But even if one player can be made better off by deviating, then it's not a Nash equilibrium. Alright, so you don't even have to check for all players. If you start checking for one player and you see that it's not beneficial, वहीं पे खत्म, उसका candidature cancel. ठीक है ना? Now let's move to another outcome, which is, let's go with quiet and fink, right? 4 outcomes हैं हमारे पास. So इस बार quiet and fink check करते हैं. ठीक है? So if it is quiet and fink, again let's think from the perspective of player 1. Okay? So now what player 1 is thinking कि भाई सामने वाला जो player है उसने fink choose कर रखा है, right? So now player 1 has to evaluate कि if the other player has chosen fink, can I do better by deviating, right? If the other player is following the action specified by this particular action profile, can I do better? How? Let's see. If the other player is choosing fink, तो हम इस zone में हैं, right? In this case, if player 1 remains quiet, which is what this action profile specifies, right? The payoff is 0. है ना? ये payoff 0 है. Whereas if she finks, the payoff is 1. तो हमको एक deviation मिल गया, not beneficial. ठीक है? Symmetric argument होगा when you have this, when you have fink and quiet. क्योंकि इस case में if player 1 is finking, right, then it's better for player 2 to also fink, right? जो argument player 1 के case में apply हुआ वो player 2 के case में भी apply होगा, right? So even your fink and quiet does not qualify. Finally, let's check for fink and fink. Okay. For fink and fink, what do we have? We see that if from the perspective of player 1, player 1, तुम ऐसे सोचो, कई बार students get confused. So when you as an economist, when you as an analyst are trying to find a conclusion, trying to find a solution to a particular situation, है ना? ये game है, इसका solution तुम्हें ढूंढना है. तो उसका ढूंढने का क्या तरीका है? तुम्हें you have to put yourself in the shoes of every player one by one, right? Because unless you do that, पहले बात तो तुम बाहर खड़े होके इसका analysis नहीं कर सकते, right? You have to put yourself in the shoes of every player one by one. In this case, the players are symmetric. तो ठीक है, चलो, I mean, whatever applies to one player also applies to the other player. But this may not be the case always, है ना? हमने वो discuss किया था the case of say matching pennies. We'll just discuss, right? So in the case of matching pennies, suppose you're modeling sibling relationship, so you have the siblings are not symmetrical then, right? There's an older sibling, there's a younger sibling. So you have to put yourself in the shoes of the younger sibling and see that given the action chosen by the older sibling in a given action profile, ये वाली sibling क्या मतलब can she do better by deviating, right? And then you have to put yourself in the shoes of the older sibling. So this is what we will be doing. Whenever you are analyzing, you will be thinking from the perspective of every player one by one, right? और जब तुम प्लेयर 1 की तरफ से सोच रहे हो तो तुम्हारे लिए क्या गिवन है? तुम्हारे लिए गिवन है प्लेयर 2 का चॉइस। ऐसे सोच रहे हो ना तुम कि अच्छा अगर इसने ऐसा किया, देखा ना वो क्या नाम है, चक दे इंडिया देखा ना, राइट? सो व्हेन यू आर strategizing in the climax scene when the क्या नाम है, the coach, right, Kabir Singh is looking at what action should be the best action, right, given what the other player could choose. Huh? So he's thinking that the other player, okay, oh my god, her left foot is like this. So I believe, right, he doesn't know. He doesn't know. So he is now, you know, thinking what would be the best action, right? Conditional on whatever other possibilities the samne wala person is, right? So he's thinking, okay, her left foot is in the front, she might take a left shot, right? So in that case, he's like, okay, the goalie should go left and defend, right? If she is putting her, hockey stick in the front, and it means that she's taking a right-handed shot. That means the goalie should go in the other direction. She should go in the right. And then he thinks that okay, no, she's going to take a center shot. She's going to take a straight shot, right? And then what is the best action that the goalie should take, है ना? तो जब हम प्लेयर 1 के पर्सपेक्टिव से सोच रहे हैं तो हम सोच रहे हैं कि प्लेयर 2 अगर ये करेगा तो क्या मेरे लिए जो एक्शन स्पेसिफाइड है वही सही है या मेरे पास बेटर ऑप्शन है? अगर बेटर ऑप्शन है मेरे पास तो आई विल नॉट डू दिस विल नॉट बी एन इक्विलिब्रियम, right? If this action profile is chosen, then I will deviate. And if I deviate, this is not an equilibrium. Similarly, from the perspective of player 2. Player 2 is thinking, सामने वाला क्या नाम है, the other player is thinking that if she shoots a left shot, I have to go left. If she shoots a right shot, I have to go right. If she shoots a center shot, I have to stay in the center. Okay? So that's how we're going to think. Alright? So now from the player one's perspective, let's start there, right? So player one's perspective क्या है? Player one को दिख रहा है कि इस action profile में, right? Player two is in this action profile. Player two is choosing Fink. Huh? So where are we now? Player two is choosing Fink. That means we are here. Correct? Player two is choosing Fink. Up for player one, if she one second, right? If she goes with quiet, if she sticks to the action specified, the action profile, she will get a payoff of 1. And if she deviates, she will get a payoff of 0. Cannot benefit from deviation. Similarly, a symmetric argument applies. If the player 1 is going to Fink, तो हम इस जोन में हैं, ठीक है? तो इस केस में if from player 2's perspective, same argument applies. If player 1 is going to Fink, if I stick to the equilibrium strategy, I get 1. If I deviate, I get 0. So that means that this qualifies. This is the Nash equilibrium. In this case, it is the only Nash equilibrium. It is unique. Got it? Right? So what we are doing is we are putting ourselves in shoes of every player and we are evaluating every possible outcome and thinking कि दोनों में से कोई भी player क्या deviate करके benefit कर सकता है, right? Okay. Now let's go ahead and do another example. The second example is your battle of sexes or the Bach or Stravinsky wala. ठीक है? So इस case में if prisoner's dilemma में the equilibrium is when both players are essentially cheating on each other. Both players are doing चुगली of each other. और उसका reason यही है कि कभी भी अगर सामने वाला चुप है, सामने वाला कोऑर्डिनेट करने की कोशिश कर रहा है, so it is in your interest to give धोखा, right? So even though there is an equilibrium over here, there is a possible action profile in which both players can be better off. That action profile is not stable. It is not an equilibrium. Equilibrium is where both are getting the almost the least possible outcome. Not 0, but almost the worst outcome. Okay. but this is an equilibrium, right? So then you have to remember that an equilibrium is no judgment of uh, social welfare. Now let's, so in this case, if you think about other examples that we were doing, right, like working on a group project, so that means that if you're working on a good group project, then both of you will shirk. हाँ? If you're modeling arms race, है ना, अभी हमने किया था पिछले सेशन में, if you're modeling arms race, that means that both the countries are going to arm themselves, they will not refrain. If you are modeling what else did we do, I think और क्या किया था हमने, हाँ हमने वो बर्ट्रांड duopoly किया था, right? So in that case it means that both the firms are going to undercut each other in terms of prices and both of them are going to land at their marginal cost. ठीक है, सो जीरो वाला आउटकम नहीं होगा जिसमें कि सबका मिनिमम पे ऑफ हो, बट वो आउटकम होगा जो कि मतलब सेकंड बेस्ट है. ऑलराइट, so now we are in the battle of sexes. We have Rahul and Anjali, and they are either in for a stand up or they are in for uh, clubbing, right? And this is the payoff that we had. ठीक है, राहुल को पसंद है stand up, Anjali wants to go to clubbing. In this case, again, let us evaluate each of the outcome, right? So if you are in the stand up, in this outcome, you see that if the other player, again think from the perspective of player 1. So if player 2 is going to stand up, if player 2 is going to go to stand up, then following the equilibrium strategy would mean that player 1 will get a payoff of 2, and not following it would mean that he'll get a payoff of 0, right? So that means player 1 will not deviate. Player 1 is not deviating. Similarly, if now we are thinking from the perspective of player 2, so if player 1 is going to be following his equilibrium strategy, that is going to stand up, right? So then we are in this zone. And then in that case, if player 2, if Anjali follows her equilibrium strategy, then she will get a payoff of 1, right? Less than Rahul, but that doesn't matter because outside of this strategy, if she follows the other action, right, then she'll get a 0, right? So even Anjali is not going to deviate. So this qualifies as a Nash equilibrium, right? Now let's take another one. The other option is here S, C. One is going to clubbing, one is going to stand up, right? So S, C may again let us look at the case where from the point of view of player 1, right? So we have that player 2 is going clubbing. So player 2 is going clubbing, that means this is where we are. If player 1 follows his equilibrium strategy according to this action profile, which is other player is going clubbing, you go to a stand up, then the payoff is 0, right? Whereas deviation will mean a better payoff, right? So it's better that instead of sticking to stand up, if the other player, if Anjali is going clubbing, just go to clubbing, right? That will be better. Okay, so then we found that a single player deviates, not an equilibrium strategy. The same argument will apply, and you will see that C, S is also not an equilibrium strategy. And finally, let's check for C, C. So for C, C, using similar arguments that we had with S, S, right? From the perspective of player 1, if you are thinking, then when player 2 goes for C, then we are here. And in this case, if player 1 follows his equilibrium strategy, if Rahul sticks to C, okay, he is going to get 1. Whereas if he मेरे को stand up ही जाना है, so he'll get a 0, right? So no deviation from Rahul. Similarly, from in the case of Anjali, Anjali को वैसे भी clubbing ही जाना था, तो अगर Rahul clubbing जा ही रहा है, so Anjali will also go clubbing. She is getting maximum benefit out of it, right? So then this qualifies. Okay, so what we have is two Nash equilibria over here. Okay, two Nash equilibria, and both of them, right, are stable. So it is not. So this is a case where the Nash equilibrium is not unique, right? So what we have is that any social order in which uh, say it's both of them are have decided, or both of them have settled on going to Rahul's favorite thing, right? To stand up, or both of them have decided to go to clubbing. It will be stable. It will be equilibrium in the sense that यूनिलेटरली अकेले राहुल को स्टैंड अप में जाके कोई फ़ायदा नहीं है अगर अंजलि क्लबिंग जा रही है एंड इफ राहुल इज गोइंग टू स्टैंड अप then Anjali cannot go to clubbing and be better, right? Because they value the coordination, they value the companionship, right? And इस case में हमने वो किया था the example that we did was, yeah, we did this example on coordination in terms of what is the party stance on a particular issue, right? So no matter what the issue is, even if all party members do not agree, it's still better that they put up a united front. So it can be that they are in a SS comma या फिर CC kind of situation. In SS, some party members, in this case suppose player 2 is worse off than player 1, right? But she is still better off as compared to what she would be if she would not coordinate. Okay, so this is a kind of situation which is asymmetric in terms of the payoffs that it accrues to every player. It is asymmetric in terms of the actions that is chosen by no, asymmetric in terms of the preferences of the players, right? But this is still in equilibrium. Both of them are equilibrium. Okay. Okay. Now let's go to the third example. Matching pennies. Matching pennies का case क्या था? This is what we had, that if both of them match, then this is the payoff. If they do not match, then Rahul pays Anjali. ठीक है, इस केस में you will find, let's start with one. Suppose you have HH. Let's check HH. HH का केस क्या है? Again thinking from the perspective of player 1. If player 2 is going to play H, right? So then sticking with the equilibrium strategy gives player 1 100, and trying something else gives -100. So player 1 is not deviating, ठीक है ना? बट हमको player 2 के लिए भी चेक करना है, हमको हर प्लेयर का इंश्योर करना है. अगर हमको दिख जाता है कि player 1 ही डेविएट कर रहा है तो कहानी खत्म थी वहीं पे. But since player 1 Rahul will not be deviating, we have to check for Anjali, right? So for Anjali, we will see that if Rahul is going to go for heads, right, then we know that for Anjali, sticking with the strategy specified by this action profile, which is H, gives her a -100, whereas choosing T gives her 100. ठीक है? So Anjali के लिए नहीं है ये stable, ठीक है ना? And similarly, when you check every combination, you will find that actually there is no Nash equilibrium. कोई भी स्ट्रेटजी में अगर, क्योंकि हमको पता है अगर तो मैच हो रहा है ना, अगर तो क्या नाम है, पेनी हेड्स हैव मैच्ड, देन अंजलि वुड वांट टू मूव अवे फ्रॉम दैट, उसकी जेब से पैसे जा रहे हैं. और अगर पेनी हेड्स मैच नहीं हो रहे हैं तो राहुल वुड वांट टू मूव अवे, because this is precisely a game in which one player is benefiting at the expense of the other player. So there will be no equilibrium like this. ऐसा कोई भाई बहन का रिश्ता नहीं होगा जहाँ पे वो सेटल कर जाएं कि लेट्स मैच करने में एक जना खुश है बट दूसरे को बिल्कुल ही पसंद नहीं है, राइट? नहीं मैच हो रहा है तो दूसरे को, then the other person with the older sibling is happy but the younger sibling does not like it, she wants to change that. So in any combination of actions at any action profile, one player will find it beneficial to deviate. Okay, so there is no Nash equilibrium in the game of matching pennies. Okay, let's also do Stag Hunt. Stag Hunt जो हमारा गेम था उसमें the only difference with Prisoner's Dilemma was that the deviation was less beneficial than coordination. Right, so this is what we had 3 comma 3, 0 comma 2, 2 comma 0, 1 comma 1. है ना? और इस केस में when you will check, let's check every outcome, right? Suppose we want to check s comma s, so s comma s में हमको दिखेगा that from the perspective of player 1, if the other player is going with, if the other player is going with s, then sticking with the strategy specified here gives 3 and deviation gives only 2. And so player 1 is not going to deviate. From the point of view of player 2, if player 1 is going to play S as is specified by her equilibrium strategy, right, then in the case of player 2, if she sticks with S, she will get 3, whereas if she goes to 2, H, she will get only 2. Okay, so this qualifies, there will be no deviation. Another one that you will find will qualify is your H comma H. ये check करना, ये भी qualify होगा, ठीक है? In other cases where one player is going for S, other is going for H, these two will not qualify. जिसमें one, if say one player is going with Stag and the other player is going with Hare, right? So it will be beneficial. Let's check that. Let's check that. Okay. Let us check the action profile where player 1 is going with Stag, player 2 is going with H. ठीक है? So इस case में player 2 has gone with H. Huh? So this is what we will be looking at, right? Now from player 1's perspective, if she sticks to the action specified by the action profile, she gets 0, whereas if she switches to H, she gets 1, right? So there is deviation. अगर सामने वाला गेम छोड़ के रैबिट पकड़ने जा रहा है तो यू वुड वांट टू गो एंड कैच अ रैबिट ऑफ योरसेल्फ, है ना? क्योंकि स्टैग के साथ रहने में तो स्टैग पकड़ाएगा नहीं, स्टैग को पकड़ने के लिए दोनों प्लेयर्स चाहिए, ठीक है? सो इन दिस केस अगेन you will have 2 Nash equilibrium. Alright, and this is the case where you have a what do you say, higher, not higher exactly, a more desirable Nash equilibrium, this one, and a less desirable. ठीक है? ये है तुम्हारा मेट्रो स्टेशन वाला इक्विलिब्रियम, सब कोई नहीं फेंक रहा तो मैं क्यों फेंकूं? ये है तुम्हारा सड़क वाला इक्विलिब्रियम, सभी फेंक रहे हैं तो मैं अपनी जेब में डाल के क्या करूँगी? ठीक है? सो देयर इज अ socially more optimal or socially optimal outcome that exists, but that doesn't mean that this is not an equilibrium. हमको दिख ही रहा है कि अगर ये equilibrium अगर ऐसा है, if this is the action profile, then this will be an equilibrium. Possibility दोनों है, but ये भी possible है कि lower level वाला equilibrium हो actually. ठीक है? Okay. Alright. Now there are a few other games that is discussed in your book. I will discuss a couple of them. Alright. 1 second. So first is your multiplayer Stag Hunt. This is simple in the sense that what this is saying is that instead of 2 players, because in 2 players what you could do is you could create that matrix and find out, right? मल्टीप्लेयर स्टैग हंट क्या है कि जैसे हमने शुरू में गेम डिस्क्राइब किया था दैट यू हैव n players. If all n players focus on hunting the stag, then the stag is caught, divided equally, and everyone prefers that outcome to any other outcome, right? However, even if one deviates, then you have that the stag is not caught. The person who deviates gets the rabbit, but the other people don't get anything, right? And the third one is that everyone catches the rabbit, right? तो हमारे पास मतलब matrix में नहीं दिखा सकते हैं, but technically the game is the same, okay? And what you will find is that in this game also the action profile where everyone chooses stag, n players हैं, सबके सबने stag choose किया है. This is an action, this is Nash Equilibrium, as well as this where everyone goes for here is also a Nash equilibrium, and it makes sense, right? In this case, no one can benefit by deviating because if any one player, suppose any player I, इनमें से कोई भी एक प्लेयर आई अगर हेयर के तरफ डेविएट कर जाता है, उस प्लेयर का अपना पे ऑफ ही कम हो जाएगा बिकॉज everyone prefers a share of the stag as compared to a rabbit, which is all to themselves, but the stag is a better deal for everyone. वैसा प्रेफरेंस ही डिफाइंड है ना. और इस केस में इफ एवरीवन इज गोइंग फॉर हेयर, तो एक अकेला कोई प्लेयर जाके स्टैग के लिए खड़ा हो उसका कोई फायदा नहीं है, हर किसी को हेयर के साथ ही जाना पड़ेगा, है ना. और बाकी जो भी एक्शन प्रोफाइल्स हैं, है ना, यू हैव अनदर एक्शन प्रोफाइल वेयर सपोज n-1 choose stag and the nth player chooses hair, will not be a Nash equilibrium क्योंकि एक भी अगर गया, है ना, स्टैग तो हाथ में नहीं आने वाला, तो हर इस n-1 प्लेयर के लिए बेनिफिशियल है टू डेविएट, राइट. सो this is the same case as S, H in our two player game. So here also you will have two Nash equilibria, a higher level and a lower level. Alright. There's another game called the Hawk and Doe. ये game क्या है? इसमें also you have two players, right? And there are two actions available for with every player. It's either to be passive or to be aggressive. Okay, this kind of models animal prey behavior. Okay, so this is something that is applied to the animal world, and it can also be applied to humans. Basically, we are worse than animals in many cases. तो इसमें situation क्या है कि every player, so suppose for player 1 you are thinking, for any player the best outcome is that, you know, पहली बात तो it is preferred that whenever let me state it this way, that whenever the other player is passive मतलब कि aggressive नहीं है, defensive है थोड़ा, ठीक है ना. So whenever the other player is passive, right, then you want to be aggressive. But if the other player is aggressive, then you are better off being passive. ठीक है. तो दोनों aggressive उनको नहीं चाहिए. दोनों aggressive is the worst outcome because they are both are going to fight and it's going to harm everyone, right? So both of them aggressive is the least desired, right? So let's put a 0,0 over here. The next is that if both of them are passive, क्योंकि होता है कि अगर सामने वाला पैसिव है तो इससे अच्छा तुम अग्रेसिव ही हो जाते हैं, ठीक है. सो द नेक्स्ट बेस्ट इज दिस, अगर सामने वाला पैसिव है, राइट, द बेस्ट आउटकम इज व्हेन यू आर अग्रेसिव. ओके, सो इन दिस केस दिस इज 2,3 and this is 3,2. What this essentially means is that for player I, the best outcome is when you are aggressive and the other person is passive. Because when you're aggressive, whatever resource you're fighting over, you get the resource. Okay? The other best, the next outcome is that when other player is already aggressive, then you are passive. क्योंकि अगर वो सामने वाला अग्रेसिव है ऑलरेडी तो लड़ाई से फायदा नहीं है, ठीक है। समझ लो कि दोनों के अब मतलब both are equally what do you say, powerful, equal, the strength is equal. Okay, so it's not like that when both are fighting one can win. When both are fighting, both lose, both are both have heavy losses, right? So if the other person is already aggressive, then you prefer passivity. Okay? Other than that, P comma P, both are passive is less preferred. The worst is when both are aggressive. Both are passive, so it's less preferred key in less preferred compared to these two, right? But it's definitely preferred over both being aggressive. So this is what I have done. I've just put numbers. इसको तुम you put this 3 2 1 0, right? This is for player I, for player 1, for player 2 ये उल्टा हो जाएगा, है ना? For player 2 ये हो जाएगा 0 1 2 3, ठीक है। तो player 2 0 1 2 3 and this is what I have put over, ठीक है। तो इस केस में भी, इस केस में you will find that again there are two Nash equilibrium, हाँ, ये तुम अपने आप चेक करना. What you will find is that the two Nash equilibria are passive aggressive and aggressive passive, ठीक है। एक बार एक का चेक ही कर लेते हैं. सपोज पैसिव एंड अग्रेसिव, इफ player 2 is going to be aggressive, right? So in that case player 1 जो है ना, if player 1 sticks to the strategy specified here, sticks to being passive, then the outcome is 2, and if instead goes to be aggressive, then the outcome, then the payoff is 0. तो player 1 deviate नहीं करेगा. Similarly, if player 1 is going to stay passive, right? In that case, what you have is that if player 2 sticks to being aggressive, she gets 3, and if she changes and goes to become passive, she'll get 1. ठीक है. तो ये ऐसा होगा कि you know in equilibrium ये वैसा हो जाएगा जैसे तुम्हारा sort of like a battle of sexes, right? So where you have what, that अगर सामने वाला passive है तो तुम you are aggressive, and if सामने वाला already aggressive है तो तुम passive हो, और मतलब शांति है, मतलब stability है, no one wants to deviate, ठीक है. Okay, now let me discuss. There's another game called coordination game, and this is a variant of the battle of sexes. Okay, so coordination game ऐसा game है जिसमें कि, so let me just discuss that. Coordination game में it's just like battle of sexes, okay, but the issue is that now Rahul and Anjali, both of them prefer stand up to clubbing, ठीक है. तो ये है stand up clubbing, both of them prefer this. पहले हमारे पास क्या था, ये 2 था, ये 1 था, और यहाँ पे ये 1 था, ये 2 था, बट अभी क्लबिंग अगर दोनों जा रहे हैं तो दोनों को 1 ही मिल रहा है. एंड ऑफ कोर्स इफ दे आर नॉट गोइंग टुगेदर देन दे आर नॉट हैप्पी, that is still the same, but both of them prefer to go to stand up, ठीक है. इस केस में भी तुम देखोगे that there are two Nash equilibrium, SS as well as CC. Both of them are Nash equilibrium. And then you will wonder कि जब दोनों का agreement है यहाँ पे, ठीक है, तो फिर भी ये कैसे होगा? How will this happen? Okay. So maybe not in a two-player game, or rather less likely in a two-player game, but when there are many players involved, then this actually can happen and has happened, does happen. Okay, so think of it in terms of, so this is essentially the kind coordination requires, मतलब जैसे हमको जैसे बैटल ऑफ सेक्सेस में हमने वो एग्जांपल किया था where we said that there are two firms who are merging and each of them use different technologies on their computers, but it is better for both of them to coordinate there, come to a single technology, ठीक है. तो उस टाइप की बात कर रहे हैं हम, जहाँ पे कि कोऑर्डिनेशन नहीं होने से दोनों पार्टीज को पसंद नहीं है, ठीक है। तो इस केस में इनफैक्ट एक्चुअली व्हाट हैपेंड इज एन एग्जांपल दैट योर बुक आल्सो हैज. सो व्हेन एप्पल कंप्यूटर्स केम, they were technologically better than IBM computers at that time, right? But it so happened that in equilibrium, everyone, so due to various reasons, हमको नहीं पता ना कि वो equilibrium पहुँचे कैसे. All we observe is that we are in equilibrium when unilateral deviations cannot be beneficial, right? So in equilibrium, it was actually observed that a majority of people actually went with IBM computers, which were technologically inferior to Apple computers, right? So people could have been here. Everyone agreed that Apple was better, but अब जिस भी रीजन से सबके सब अगर IBM यूज करने लग गए, तो then you cannot switch to Apple because you require some degree of compatibility across devices, right? So if most of the firms are using IBM computers, then तुम अकेले Apple use करके तुम you will face is coordination issues, ठीक है? So even though this is superior, this is nonetheless an equilibrium, and it is also possible that this is actually reached, ठीक है? All right. So now let us discuss what is called the best response function. So far what we have been doing is हम एक एक आउटकम को जो है एक एक आउटकम को स्टडी कर रहे हैं. हम देख रहे हैं इसमें क्या है, यहाँ से डेविएशन हो रहा है क्या, यहाँ से डेविएशन हो रहा है क्या, राइट? सो that is something that is cumbersome first, and second, as you increase the number of actions available, as you increase the number of players available, ये करना और ही और मुश्किल होता जाएगा, कर ही नहीं पाओगे. I mean the cases that we have considered are just 2-player 2-action games, उसमें कर सकते थे, ठीक है. तो हमको थोड़ा और सिस्टमैटिक तरीका चाहिए. तो उसके लिए हम we will construct what are called best response functions, ठीक है. The idea is similar. So we are actually starting at, हमको क्या चाहिए इक्विलिब्रियम में, कि इक्विलिब्रियम में every player is choosing an action that is maximizing her payoff, ठीक है. यही तो हम कर रहे थे. सामने वाला अगर मान लो कि फिंक चूज कर रहा है, तो हमने वो कॉलम हाईलाइट किया, फिर हमने कहा कि उस कॉलम में अगर इक्विलिब्रियम स्ट्रेटजी के साथ खेलेंगे तो ये मिलेगा, डेविएट करेंगे तो क्या मिलेगा, ठीक है. तो इसको ही हम यही वाले फंडा को लेकर चलेंगे, और इस ये यूज करने से we will not have to evaluate every possible outcome, ठीक है. So let us do with some notation, right? So every player is thinking what? Every player is thinking कि given सामने वाले का action choice, what is my choice of action from the action set that is available to me? What is my choice of action that will maximize, or that will give me the maximum payoff, right? Or in other words, what is my best response to any given action of the other player, right? So यही हम इसको एक formal functional form में करेंगे. So the notation that we'll go with, we'll denote it using best response function of player I, right? B is for best response function of player I for actions of players other than I, है ना. ये वाला notation हमने पिछले सेशन में किया था. So given, so the argument in this function, right? The argument is this, जो हमारा x वेरिएबल जाता है, और जो y वेरिएबल हमारा फंक्शन थ्रो आउट करता है is an action from the action set of player I, है ना. So player I का action set क्या है? AI, action set of player I, right? So in case of prisoner's dilemma, this AI will essentially be equal to quiet and fake, ठीक है. तो सामने वाले प्लेयर का जो एक्शन है उसके बेसिस पे this function will throw out, right, or this function will come up with an action, right, from the action profile of player I. Okay, so the argument in the function is the action of other player. The product or the map. This function maps other player's action to my own action. Right? So let's write it formally. What we have is that the best response function of player I given other the action of the other players is essentially an action AI which belongs to the set of actions AI, right? Such that these two dots are symbols, but such that the utility that player I derives from AI, given that the other players are choosing AI, A minus I, is greater than the utility that player I derives from AI prime, given that the other player is choosing AI, greater than equal to, ठीक है? For all AI, for all, one second, for all AI prime in AI. ठीक है? ये notation को I'm repeating again. What it says is the best response function takes as an argument what the other player is doing, right? And gives an action out of player I's own action set. Okay, so ज़रूरी नहीं कि वो action unique हो, but let's start with the case of a unique action. So this is giving that this function is an action AI from the action set of player I, total action set, such that the utility that player I derives from playing AI, given that the other player is sticking to A minus I, is at least as much as the utility that is derived from playing any other action, given that the other player is choosing still A minus I. And this should be higher than any other action, है ना? तो यही लिखा है कि for this is the symbol of for all, right? So for all such alternative actions in player I's action profile, this should hold. अगर ये hold करता है तो ये वाला जो है AI, this is then the best response of player I to A minus I of the other players. Alright. So, for example, in the Battle of Sexes, what you had is that Battle of Sexes में था that suppose the best response of player 1, suppose Rahul, best response of player Rahul when Anjali plays clubbing is clubbing, and the best response of Rahul when Anjali goes for stand up is stand up. ठीक है? इस केस में ये सिंगलटन सेट है, मतलब कि एक ही एक्शन है. ऐसा हो सकता है कि मतलब जब she goes for stand up, if the payoff functions are such, then both clubbing and stand up give the same payoff. तो वो दोनों ही बेस्ट रिस्पॉन्स फंक्शन में आ जाएंगे. ठीक है? So using this, we can give an alternative definition of Nash equilibrium. Right? So Nash equilibrium क्या है essentially? जहाँ पे हर कोई प्लेयर डिविएट नहीं करना चाहता है ना? कोई प्लेयर डिविएट कब नहीं करेगा? जब दूसरे प्लेयर का जो भी एक्शन है, हाँ, उसके बेसिस पे सपोज प्लेयर जे का जो भी एक्शन है, given that if player I is choosing the best response, then player I will not deviate. And if player I is choosing a response that is not best, that means that there exists any other AI such that which gives a higher payoff, right? अगर ये hold नहीं कर रहा है तो कोई AI prime होगा जो higher payoff दे रहा है, तो higher payoff दे रहा है तो deviation होगा, है ना? So just using this logic, we can redefine, or we can alternatively define Nash equilibrium as an action profile A star right? An actual profile A star is a Nash equilibrium if and only if for every player I this holds that your AI star में जो भी action है that belongs to her best response to the action specified for other players in this action profile. Okay? So given that I have already spent a lot of time explaining the notation, this should be clear. This is just another way of stating that every player is, no player wants to deviate, and that just means that if other players are doing what the equilibrium strategy specifies for them, then the equilibrium strategy or equilibrium action specified for player I is the best response. If it is not, then it will not be part of an equilibrium. मतलब player 1 will deviate. Okay? Okay, so just to simplify, if there are two players, so in the specific case, when there are two players and two actions, ठीक है, तो हम इसको लिख सकते हैं कि सपोज हर क्या नाम है बेस्ट रिस्पॉन्स सेट में इस केस में हमारे पास सिर्फ एक ही एक्शन था which was part of the best response set. Suppose that is the case, that the best response set is singleton, मतलब एक ही एलिमेंट है उसमें. Then we can write that A star is Nash equilibrium if we or rather A1 star for player 1, this is the best response to A2 star, and for player 2, A2 star is the best response to A1 star. ठीक है? तो अब इसको अप्लाई करके now let us solve the 4 games that we have done. You will see how simple it becomes. हर को evaluate करने की ज़रूरत नहीं है. Now we will simply solve each of the games using the best response function. ये तुमने किया तो होगा ही. So let's do it quickly. First of all, let's start with prisoner's dilemma. ठीक है? I'm assuming that you do not know because I've seen a lot of students get confused about this. So you have your quiet and think, and you have 2, 2, 0, 3, 3, 0 and 1, 1. ठीक है? तो अब हम इसमें क्या करेंगे कि हम बेस्ट रिस्पॉन्स निकालेंगे. लेट अस स्टार्ट विद प्लेयर 1. हम अभी निकालने वाले हैं प्लेयर 1 का बेस्ट रिस्पॉन्स टू एवरी पॉसिबल एक्शन ऑफ द अदर प्लेयर. फिर से हम वो चकदेड़ने वाले फ्रेम में, सामने वाला अगर उसका लेफ्ट फुट आ गया है तो बेस्ट रिस्पॉन्स क्या होगा, गोली शुड मूव लेफ्ट. सामने वाले का राइट फुट आ गया है तो बेस्ट रिस्पॉन्स है ये. सेंटर खेलने वाली है तो बेस्ट रिस्पॉन्स है. ठीक है? उसी तरीके से सोचना है, कबीर खान के तरीके से सोचना है ना. तो नाउ यू आर प्लेयर 1, right, and you are thinking that if player 2 is going to play quiet, that means that you have to look at this column. If player 2 is going to keep quiet, what is my best response? 2 या 3? 3 is higher, so you underline 3. underline करना है, स्टार करना है, ऊपर लाइन करना है, जो भी करने का तो मार्क करना है उसको बस. ठीक है ना? So if player 2 is going to be quiet, my best response is to think because that gives me a higher payoff, right? इस केस में एक चीज याद रखना, this becomes very confusing कि तुम कौन सा नंबर देख रहे हो. Remember, this here is player 1. These are the actions of player 1. This here is player 2. These are the actions of player 2. Or by logic, the column over here is where player 2 chooses to be quiet. The column over here is where player 2 chooses to think. And since you're thinking from player 1's perspective, the number that you will be comparing across are not these numbers, right? ये नहीं compare करना है, तुमको ये compare करना है. Okay. You need to compare these numbers, the first numbers. ठीक है. So here you find that if the other player is going to think, if player 2 is going to think, then we are in this column, right? Okay, and in that case player 1's best response is to stay quiet or to think, right? So we have an underline here and we have an underline here. Okay, this was the analysis from player 1's perspective. अब कबीर खान की तरफ से सोच लिया, अब तुम्हें सोचना है वो क्या नाम है ऑस्ट्रेलियन प्लेयर की तरफ से. ठीक है, सो ऑस्ट्रेलियन प्लेयर की तरफ से तब तुम सोचोगे तो तुम्हें क्या देखना है भाई कि नाउ व्हेन प्लेयर 1 is choosing quiet, player 1 is choosing, if player 1 chooses to be quiet, right, then इस वाले रो में हो तुम, and now you have to evaluate payoffs of player 2, which are the second numbers in every cell. So compare 2 with 3, 3. ठीक है, and then when you are when now player 2 ने सोचा कि अगर वो quiet रहता है मेरे लिए best है to think, and if player 1 is going to think, right, then the best for me is to compare 0 with 1 is to think again, right? ये दोनों sorry, these two are the best responses of player 2 to different actions of player 1. Okay, and then what do we find? We want that in equilibrium every player's action should be a best response to the other player's action, and that is here. Think. You know? So that's as easy as that, right? So then you have your equilibrium, और कुछ बाकियों को evaluate करने की जरूरत ही नहीं है. एक बार तुम्हें practice हो जाएगा तुम ये फटाफट underline कर लोगे. ठीक है, तो बाकियों को evaluate करने का point ही नहीं है. तुम्हें दिख गया है कि सिर्फ यहीं पे one's choice of action is best response to 2, 2's choice of action is best response to 1's action. For every other place this does not. ठीक है, फटाफट. Now let us do the battle of sexes. So we have Rahul and Anjali deciding upon stand up and clubbing. All right, we have 2,1, 0,0, 0,0 and 1,2, right? And now thinking from say Rahul's perspective, okay, if Anjali is going to go to stand up, right, so Rahul is better off going to stand up because comparing 2 with 0, so 2, right? If Anjali is going to go to clubbing, then Rahul is better off going to clubbing. Okay, now thinking from Anjali's perspective, so what we have is that if Rahul is going to go to stand up, correct, so Anjali के लिए best यही है कि वो भी stand up जाए, and if Rahul is going to go to clubbing, तो फिर अंजलि के लिए तो clubbing ही best है. ठीक है, so again we find that these are the two Nash equilibrium. All right, okay. So similarly, I'm sure that now you can do your matching pennies and Stag Hunt, right? Let me just give you an example of a game that has more than 2 actions. Right, so you have your left, center and right are the action set of player 2, and for player 1 you have top, middle and bottom. So now the action sets are not equal. These are the payoffs for every combination. Okay, so now I'm not going to highlight, I'm just going to keep on underlining, right? So from player 1's perspective, if player 2 is going to choose L, the best is to go with M. If player 2 is going to go with C, the best is to go with T. If player 2 is going to go with R, the best is, there's no best. So in this case, the best response function actually is not a singleton set. You have three, all three of them are giving equal payoff, right? Now thinking from player 2's perspective, If player 1 is going to play T, then the best is to go with C. If player 1 is going to play M, the best is to go with L. And if player 1 is going to go with B, again, there is no unique बेस्ट रिस्पॉन्स. ठीक है, तो अब हमारे पास क्या हो गया, हमारे पास एक इक्विलिब्रियम ये है, एक इक्विलिब्रियम ये है, एक इक्विलिब्रियम ये है. जहाँ जहाँ डबल अंडरलाइन है वो इक्विलिब्रियम है, क्योंकि उस जगह पे फिर कहीं भी डेविएट करके कोई वहाँ से बेटर ऑफ नहीं हो सकता है. ठीक है, ऑल राइट. सो नाउ let us get to the final component. I really encourage you that you solve the other games that are there in your book. मतलब जो भी matrices हैं या जो matching pennies है, stag hunt है, वो सारे you should solve and you should practice. So now let us discuss what are called dominated actions. ठीक है, dominated actions क्या हैं? Let's first of all discuss what is the concept of strict domination. Right? Strict domination is nothing but कि suppose दो action को तुम compare कर रहे हो, ठीक है, और you are looking at which gives a higher payoff for every other action of the other player. ठीक है, so I'll give you a definition and then we'll do an example that will make things clear for you. So strict domination is suppose you have an action AI double prime. ये सारे actions you're thinking from the perspective of player I. उसका जो भी एक्शन प्रोफाइल नहीं, एक्शन सेट है, जो भी उसके पास अवेलेबल एक्शन है, उसमें एक एक्शन है ए आई डबल प्राइम और एक एक्शन है ए आई प्राइम. सो नाउ ए आई डबल प्राइम इज सेट टू स्ट्रिक्टली dominate AI prime if the utility that player I gets from AI double prime given A minus I, मतलब बाकी player का कोई action is greater than, right, the utility that player I gets from AI prime under the same set of action, but this applies for all actions of the other player. Okay, so let me do an example. So what this essentially means is that, let me just write a corollary and then we will do an example. Corollary मतलब अभी तक हमने जो किया है उसका और ये strict domination का जो concept है उसका एक side result है. वो ये है कि अगर देखो इस केस में you have your AI double prime. AI double prime strictly dominates AI prime. So AI prime is called strictly dominated. ठीक है, स्ट्रिक्टली डोमिनेटेड है किसी एक एक्शन से, किसी एक दूसरे एक्शन से. अगर एक एक्शन is giving worse payoffs, right, in every scenario, in every possible action choice of the other player, then that is a strictly dominated action. Okay, so then a corollary means that a strictly dominated action, मतलब ये ऐसा AI prime जो है cannot be in any Nash equilibrium. ठीक है, और ये लॉजिकल है, राइट. अगर कोई Nash equilibrium है उसमें कोई भी किसी भी प्लेयर के लिए एक ऐसा एक्शन नहीं हो सकता है स्पेसिफाइड which is strictly dominated by any other action, because that means that for every action of the other player there is an action that exists in player I's profile, in player I's action set that will give a better payoff, right. So कोई भी जो क्या नाम है Nash equilibrium है, पहले तुम मतलब you can just eliminate any strictly dominated action, it will not be part of any Nash equilibrium. तुम अपना जो अगर मान लो कि ऐसा है कि you have more than 2, 3, 4 actions हैं, बड़ा सा matrix है, तो you can start by eliminating strictly dominated strategies, right. So let's do an example. So suppose you have a case like this where You have the strategies of player 1 as top, middle, bottom, and player 2 as left and right, and you have. So I'm just writing the payoffs of player 1 because we will only be making comparisons for player 1. एक ही का करने का काफ़ी है, एक ही player के perspective समझना enough है, right? So what we have over here is that in this case you will see that if अभी just forget about B, right? अभी B को एक सेकंड के लिए भूल जाओ. If player 1 chooses L, sorry, if player 2 chooses L, right, the best action that player 1 can choose is 2, right, and if player 2 chooses R, the best action that player 1 can choose is M. So what we have here is that M strictly dominates T. T is a strictly dominated action and it will not be a part of any Nash equilibrium. ठीक है. अब दूसरी important चीज ये है कि अगर कोई action, in this case your M, is strictly dominating any other action, in this case your T, that doesn't mean that it cannot be strictly dominated by any other action. Okay, so just if I just change the payoffs over here and I make it instead of 1,3, I make it 3 and 2. So abhi ye bhul jao. These are the new payoffs, right? In this case, what you will find is that your M dominates T, right? M is strictly dominating T because no matter what the other player chooses, the other player chooses L, M is better, other player chooses R, M is better than T. Lekin, other player chooses L, B is better, other player chooses R, B is better, then M also. ठीक है ना? So B strictly dominates your M. तो अगर कोई एक्शन स्ट्रिक्टली डोमिनेट कर रहा है इसको, इट डजंट मीन कि इसको कोई स्ट्रिक्टली डोमिनेट नहीं कर सकता है, कर सकता है और करेगा भी. ठीक है. So strict domination doesn't mean, so it's not enough that you find an action that strictly dominates any other action. Okay, that doesn't mean it can be part of a Nash equilibrium. In this case your M will also be strict enough. ठीक है. So इसको तुम मतलब by elimination only you will know that the other player will choose B. Alright. The final concept that we will do is what is called the weak domination. So this is just a variant of strict domination where we have that weak domination essentially means, again, you have AI double prime and it weakly dominates AI prime for player I if एक ये तो है that UI from AI double prime comma A minus I is greater than equal to. यहाँ पे हमारे पास strictly dominated में था strictly greater than. Here it is greater than equal. Then the utility that it player I gets from AI prime given an action choice of the other player, and this applies to all action choices of other player. यहाँ से when you are comparing utilities this and this, ठीक है, ये और ये कहाँ गया, इस और इसके कंपैरिजन में इसके और इसके कंपैरिजन में ये AI प्राइम सेम रहेगा. ठीक है, बट you have to make this comparison for all possible A minus I. ठीक है. So it should be the case that for all A minus I this holds, and for at least one A minus I this holds with strict inequality. ठीक है. So इसको भी it's better to understand with an example. Again you have your T and B and you have your L and R. ठीक है. So now what you have is M, when player 1, when A minus I is L, right? Then M is better. When A minus I is R, then M is not better, right? It is equal. तो ग्रेटर देन इक्वल टू हमेशा है, ग्रेटर देन इक्वल टू हमेशा है, एक केस में एटलीस्ट वन केस में ग्रेटर देन है, ठीक है. सो देन दैट मीन्स दैट M weakly dominates T and B weakly dominates M, ठीक है ना. ये देखो, when L is chosen, so this is with equality, right? But when R is chosen, then at least एक case में the inequality is strict. So B weakly dominates M. But you also find that B strictly dominates T. क्योंकि 2 is greater than 1, 1 is greater than 0. Right? So what you can now conclude is that in any equilibrium, in any Nash equilibrium, since T is strictly dominated, T will be out. T नहीं होगा, इन दोनों में ही होगा कुछ. और M को तुम रूल आउट नहीं कर सकते क्योंकि M strictly dominated नहीं है. Alright? So it will be a choice between M and B, and of course it depends on कि सामने वाले player 2 के payoffs क्या हैं. But from player 1's perspective, there will be no equilibrium in which player 1 chooses T. ठीक है? All right. So there is one more thing that I would like to discuss, which is nothing. Since we have now discussed strict domination and weak domination, there is another concept which is called a strict equilibrium and a non-strict equilibrium. Okay. So a strict equilibrium is where a deviation makes a player strictly worse off. Okay? That's a strict equilibrium. For example, in the case of prisoner's dilemma, right? If you deviate from fink, you will be strictly worse off. But in this case, suppose there is an equilibrium. Suppose there is an equilibrium in which player 1 का action है B. ठीक है? So if player 1 deviates, player 1 का action है, suppose there is an equilibrium BL. Just hypothetical. BL के case में you will see that if player 1 deviates, right, player 1 will not be worse off. Same ही रहेगा. ठीक है? So this kind of an equilibrium is what is called a non-strict equilibrium. Okay? A strict equilibrium is where, like in the case of prisoner's dilemma and the equilibria that we have done so far, any deviation means that the deviator is strictly worse off. A non-strict equilibrium is a case like this, where a deviation could mean that at least one of the players is not worse off getting the same pair, but कोई other player worse off हो रहा होगा, इसीलिए वो पिक है वहाँ पे. ठीक है? ज़रूरी भी नहीं है, हो सकता है कि दोनों ही कोई worse off नहीं हो रहे हैं, but because it is a part of the it's a part of the best response set, then that is also an equilibrium. ठीक है? क्योंकि कोई better off नहीं हो रहा है, but कोई worse off भी नहीं हो रहा है. So there is no reason for any parties to deviate. There's a complacency, there is a stability, and that's what equilibrium is all about. Okay, so a strict equilibrium, right, cannot have of course it cannot have a strictly dominated strategy. कोई भी equilibrium नहीं होगा. But a strict equilibrium will also not have a weakly dominated strategy. क्योंकि strictly हमको चाहिए कि deviation में बंदा worse off ही हो. So basically strict equilibrium cannot have weakly dominated action for any player, right? But a non-strict equilibrium allows for weakly dominated actions. All right. So That's it. So we have covered everything in OSPON, and we have covered the Nash equilibria in what is called pure strategies. Alright. From the next session now, we are going to move to Watson, and we are going to look at cases where the strategies are not pure, and you'll see what it means. Okay, so we'll see that even when games like matching pennies do not have a Nash equilibrium, they do not have a Nash equilibrium in pure strategies, but they do have a Nash equilibrium if we modify the concept of equilibrium and actions. All right. So that's it for this session. I will see you in the next session. Bye bye.